The theme of this talk is the history of Ethereum L2 scaling solutions. And we're going to go through the history, what it looks like today. So the history of anything is always kind of a tricky area. You don't read these links, but the point of this slide is to show you that I did a bunch of cross-referencing to make sure that the knowledge that I had was actually factual. So if you want to reference the docs later, here you go. If you want to debate anything with me, I'm welcome for fighting after work. Okay, I'm going to start us off on something super easy to make sure we're all on the same page. Ethereum has some scalability issues. There are two main goals of scaling. The first is to increase transaction speed and transaction throughput. Ethereum is at about 15 transactions per second right now. Visa is about 1,700. And we also don't want to sacrifice on decentralization and security, right? We want to keep the barrier to entry low for node operators so that we don't concentrate node operating power into the hands of the wealthy, the elite, the connected. So there are two ways to scale. One is we can increase transaction capacity with higher gas limits. Ethereum's not really about bigger blocks in the way that Bitcoin is. It's about a higher gas limit inside of the block. This is what BSC and Polygon do. They fork ETH and they increase the gas limit inside of the block, which compromises on some decentralization in favor of higher capacity. For mainnet, just increasing gas limits isn't great because higher gas limits need more resources and are therefore more expensive and are therefore more inclusive and are therefore less, they compromise again on decentralization. The sharding that's going to come in the consensus layer, also sometimes called ETH2, is going to help with this. The other thing we can do to help scale Ethereum is to change the way that we interact with the blockchain. We can take some of the activity off-chain. And for this, we have a whole sea of scaling solutions. Why so many? Well, they help us do different things, just like different modes of transport help us do different things across different bodies of water. So we've got a whole ecosystem of protocols to help with this. The reason that sidechains and L1s are together is because technically they're the same thing. And channels aren't really a thing today, although they aren't dead, and same goes for Plasma. So some of these logos you might recognize, some of them might feel outdated, but here they are. So we're going to start with a really quick run through of just some key events in the chronology of the Ethereum scaling solutions, and then we'll dive deeper into the more prominent ones. In 1985, this mathematical concept of zero-knowledge proof was first introduced. And then in 2013, Coin Witness emerged with snarks for Bitcoin. Later that year, a significant advancement to non-interactive ZK proofs was made. Note here that it will be important for us to distinguish between interactive and non-interactive proofs as this presentation goes on. Then in 2014, the Ethereum white paper was published. Later that year, Vitalik wrote about Ethereum scalability issues and surfaced the idea of alternative scaling solutions. Ethereum wasn't perfect when it first launched. Vitalik knew this, we knew this. Truthfully, nothing is perfect upon inception. Then in 2015, students at Princeton came up with an interactive Arbitrum-based fraud proof. They called it Arbitrum, and that is the foundation of what Arbitrum is today. Later that year, Ethereum officially launched. Then this thing called channels emerged as a blockchain agnostic scaling solution. The two most prominent types of channels are state channels and payment channels. Then in 2017, Plasma emerges as a very, very hyped up solution to Ethereum scaling woes. The world was just really hungry for more efficient and cheaper Ethereum, and everyone really rallied behind Plasma. Then in 2018, a Plasma-like construction with bundled or rolled up transactions came into the world. Instead of having to trust an operator, valid blocks are confirmed with proofs called snarks. The snark made it almost impossible for an operator to post fraudulent transactions. So this is a really big deal and exciting for people. Then in 2018, Arbitrum argued for interactive fraud proofs as the path forward. In 2019, Merge Consensus entered the world for non-interactive fraud proofs. Merge Consensus was later renamed to Optimistic Ethereum. And just looking at the four major categories of different scaling solutions, we can see some differentiating factors. Channels are plausible for general purpose, but really just not great. You can technically do it, but this doesn't make a lot of sense. Plasma is pretty application specific as well. Rollups and L1s are great for general purpose, and of course, with L1s and sidechains, you don't inherit Ethereum security model, which we're all here, so therefore we all probably are pretty bullish on it. So now let's dive into channels, which came onto the screen circa 2015. Channels are kind of like getting into a club. There's a bouncer that you pay a cover charge to, and he forces you to sign a multi-sig contract. And the party can't start until everyone is there. And once the door closes, no one else is allowed inside. So I don't know. I don't club very much. Maybe this is like a Gen Z club. Maybe this is more like a cult. But the point here is that the part of the blockchain is locked with multi-sig. And once you're inside the club, the cool thing is that you can transact as many times as you want without paying for a blockchain transaction. In our example, our club goers are trading Pokemon cards. The key point here is that participants are updating the state themselves before submitting the final state to the mainnet. Then, when somebody wants to leave the club, everyone has to leave and has to pay a cover charge to exit. So maybe it is more of a cult club. This analogy is kind of dwindling away, but I liked it at the beginning. So if everyone isn't online when you want to exit the club, though, there's a 7-day waiting period for withdrawing the funds. The key point here is that we have the 7-day withdrawal period in case anyone tried to post a fraudulent update, or maybe there's a technical failure and you want to give a time period to dispute it. This is also foreboding for optimistic rollups in the future. Channels are useful when, one, you want instant trustless transactions, and also when you want to disintermediate transactions because you want to do a lot of state updates. You want to trade Pokemon cards a lot. Once two parties have established a channel, you can exchange value without needing to involve a third party, which isn't true with rollups today, who always need a rollup operator. Examples of channels are, for example, if you want to require a user of the Infura API to pay a small amount of ETH per API call, right? Imagine paying gas fees every time you try to make an API call. That would be ridiculous. Or if you want to do something like build a centralized ISP where you allow users to buy bandwidth from their neighbors and pay for each megabyte as they can consume it. Again, would be wild to pay for gas fees for that. Channels are limited because they aren't great for general EVM contracts, and you need to know the number of participants up front. They cannot be used to send funds off-chain to people who are not yet participants, which is a constraining factor, and it requires a large amount of capital to be locked up ahead of time. And it requires participants to be available. Someone has to be online until the channel is closed to make sure that the new state is sent to the blockchain. So you could lose all of your funds if you go off the internet, which is why people will pay other servers to maintain the ledger for them. So we got some pros, we got some cons. What can we do better? Plasma. The initial Plasma paper was very dense and vague and complex. So for round 2, Vitalik put out a much easier to understand spec of this thing he called the Plasma MVP. So Plasma looked to Gandhi, ignored all the he might be a sketchy person stuff, and decided that it was going to be the change you wanted to see in this world. Plasma has 4 key components. 1, it reframed blockchain computations as a set of MapReduce functions, which made it a lot more efficient. 2, it allowed for smart contracts to be composed on mainnet with fraud proofs. Fraud proofs also, keep that word in mind. We'll hear it a lot later on. And it allowed a parent blockchain to make infinite children copies of its chain, which of course helps with scaling. Instead of requiring unanimous consent to agree on a chain update, like channels do, Plasma assumes that all updates are accurate and then has a way to dispute any disagreements. So if 2 parties are in a channel and both parties give unanimous consent for an off-chain update to be both parties need to give unanimous consent for an off-chain update to be valid. This is channels. In Plasma, you don't have this requirement for unanimous consent, which is actually a very convenient thing that was developed. This means that an invalid update can occur without a user having any direct evidence. The Plasma guarantee is that even in this case, users still have the required off-chain data to prove and secure ownership of their assets via something called an interactive dispute game. So Plasma MVP was useful because it was more general purpose in channels, although it didn't have full smart contract support. And the whole unlimited children blockchain thing helped a lot with faster transactions. It also addressed this idea of data unavailability. So if an operator wanted to withhold data, users could still get their funds back. You weren't completely reliant on the operator being good. And it prevents front running by organizing things by timestamp, which is also something we see down the line. Plasma MVP was limited because each user still has to monitor and verify all the transactions on the Plasma chain, which is a huge overhead. And it has this long withdrawal period of about a week. It also has this thing called a mass exit problem. So if all users need to exit a Plasma chain, then the entire valid state of the chain has to be posted to mainnet within a single challenge period. Which means because of all these, remember, we have all these unlimited children blockchain copies, so the Plasma chain can get arbitrarily large. With ETH blocks already at near capacity, it became almost impossible to actually do this. So yes, in theory, you could pull all your funds off, but actually you might get stuck. So then we had Plasma Cash. It's kind of Plasma MVP 2.0. Plasma Cash was this new interactive challenge system that allows users to easily withdraw funds in case of operator misbehavior. It utilized a new Merkle tree construction called a sparse Merkle tree, and users could easily authenticate a coin's history and ownership using something called inclusion proofs. In case of operator misbehavior, a user would only need to post on-chain proof that they currently own the coin, which just consisted of 2 of the most recent transactions of their corresponding inclusion proofs. So it was useful, Plasma Cash is useful because it solved some of the Plasma MVP issues like mass exit, and it also added in the sparse Merkle tree, which allowed users to easily get their funds back in case of operator misbehavior. It was still limited though because it required users to remain online at least once every 2 weeks to catch fault withdrawals during those challenge periods. It had huge storage requirements, smaller than MVP, but still significant. And losers use fungibility or the ability to make arbitrarily denominated payments. So, yay, better, but not perfect. Can we make things even better? Now we come to rollups plus snarks. So rollups provide blockchain scaling by moving execution into a different domain. Right? Transaction data is posted on the main chain, but the transactions aren't executed there. Instead, they're executed on the rollup network, and periodically a commitment of the current rollup state is posted back to the main chain. This means that the mainnet nodes are no longer required to execute the transactions, which reduces their load. So just as confidence in layer 2 was hitting a low with Plasma not quite delivering on everything we hoped and dreamed it would be, a GitHub repo named roll_up was made public by Barry Whitehat, who's also a speaker at this conference. A cool thing about this presentation is a lot of the names in the history are actually speakers in this conference. And so he posted this repo, and it was a new type of layer 2 solution, a Plasma-like construction that I mentioned earlier with these bundled up transactions, where instead of relying on operator trust, the correctness in the bundle would be attested using an on-chain proof, which was called the snark. So yes, Plasma wasn't quite living up to the hype, so Rollups stepped in. In Rollups, execution is moved off-chain in all Rollups, and then it's bundled together, and just the transaction data is posted on the mainnet. Plasma and channels are what are called full layer 2 schemes. They move both computation and data off-chain. Rollups are more of a hybrid layer 2 scheme. They move computation and state storage off-chain, but they keep some data transaction on-chain. That means that they're allowed to use Ethereum as a data availability layer. Now, let's dive into ZK proofs. I'm going to explain how ZK proofs work, but honestly, I don't fully understand the math, and truthfully, pretty much no one else does. You need a few PhDs in advanced cryptography to really get it. There are also a lot of different types of ZK proofs. My brain melted many times preparing for this presentation and trying to read them. I'm about to show you something called an NP-complete problem. You might have learned about it in your algorithms computer science classes, maybe not. It's fine for this presentation if that word means nothing to you. And ZK Rollups actually use something called zero succinct proofs instead of zero knowledge proofs, but this is still useful to explain how zero knowledge works. Cool. So here we've got this block where all of the rules are that the only valid components of the block are the colors red, orange, and green. And in this block, Bob promises that his block is valid. He says, hey, I promise my block is good to go, but I don't want to reveal my whole pattern to you because that's a secret. This is my secret formula. So Alice says, okay, I'm going to choose 2 squares at random to make sure that they only have valid colors. She chooses 2. Cool, they're valid. Note the top red one in the corner. So then she chooses 2 more again, but now the top one is different, right? So we have to randomize the colors every time. We have to randomize the location because otherwise Alice could be able to choose them and then later figure out the whole pattern. So then Alice chooses 2 more. And Alice will keep doing this over and over again until the probability of her having seen all of the blocks and knowing that they all have a valid color is low enough to accept. And then the proof is complete. So this is roughly how ZK proofs work. ZK rollups are useful because they can avoid Plasma's exit games and challenge periods, and they don't need users to stay in line to monitor the chain. Very convenient. In theory, it solves all of Plasma's issues without trading off on security, which is also very cool. It can scale to about 2,000 TPS, and there's no withdrawal waiting period. ZKs are limited because validity proofs are very expensive to produce. They're very cheap to execute, but expensive to produce. And they can't handle general smart contracts very cost effectively. Also, generating ZK proofs is very mathematically complex. So today, they're limited to a few simple transactions. Now we're getting to optimistic rollups. So like Plasma, optimistic rollups have this thing called fraud proofs. Unlike Plasma, they publish transaction data on-chain, so any observer can reconstruct the state and detect invalidity. If the block is found invalid, it will be inverted, and in order to incentivize good behavior, you have to post a bond to issue a block. If your block is invalid, then your bond gets slashed. In 2019, Harry, who's one of the founders of Arbitrum, and Vitalik engaged in a very friendly public Reddit debate about interactive versus non-interactive proofs. They both have their pros and cons. Today, interactive proofs seem to be the winner because non-interactive proofs had some fundamental bugs that made the approach just not very viable. They're called time travel and reality distortion attacks, if you want to Google about those later. I can also give you a link in my little bibliography. So I'm going to explain to you how interactive optimistic fraud proofs work today. Because interactive fraud proofs are really the type of fraud proof that exists today and is we're moving forward with. This style of interactive fraud proofs makes the L2 participants do majority of the work on the L2 side before executing something on mainnet. So Alice submits a block that contains 10 to the 10 bundled transactions. And Bob shows up and he wants to dispute Alice's claim. Bob then breaks up Alice's claim into segments. Of Bob's segments, Alice chooses the first section that she disagrees with. Then Alice takes that section and breaks it up into more subsections. Then Bob chooses a section within Alice's section and breaks that up into more subsections. Then Alice chooses a chunk she disagrees with, and so on and so forth. And they keep doing this until there's only a single step of execution left to dispute. That's why it's interactive. Bob and Alice are going back and forth until they find the specific single part of the execution that they disagree with. Then they ask a referee, which is the mainnet in this case, to rerun just this one execution step. Instead of having to re-execute the entire chain, you end up with a much more efficient way of resolving disputes. The referee actually does a bunch of things along the way, checking in at various stages, but this is the best way to simplify it. So optimistic rollups are useful because they don't require users to monitor their own coins for safety. They can scale to about 500 TPS. They're cheaper than ZK, and devs don't need to be advanced cryptography experts to code it. So porting over L1 apps is pretty easy. They are still limited because there's this 1 week withdrawal period, which can be very inconvenient. For that, there are fast liquidity providers. So really, in summary, rollups today are the leading scaling solution for Ethereum. It's kind of the thing everyone's getting behind. They're both optimistic and ZK rollups. Both have pros and cons. Rollups are the next evolution of blockchain technology, but they're built on years and years of arduous labor by people who built all of their predecessors. So really anything that exists, in science, in math, is always built on the shoulders of giants. So that's kind of the point of this presentation is we didn't get here from nowhere. We got here from people bashing their head into the computer for years on end. That's it.
So we have time for at least some questions. So any questions? Come on. Okay. Does it work?
Thank you. I'm really pleased nobody threw a box at me that I had to drop on the first morning. So we come from a company called Nami, and when you mentioned channels early on, around 2018, we had our own version that doesn't appear in the conference, I'll be honest. So we feel a little bit like we've come into the lion's den in some ways.
Maybe you can be the change you wish to see in the world.
Maybe.
Bring it in.
I completely agree with the sketchy Gandhi thing, by the way. So what we did was something slightly different. We did what we call state pools. So it's a combination of state channels and pool deposits. Fixes most of the things that you've mentioned there about channels. I just wondering whether, you've obviously done a huge amount of research and it was a great presentation. I'm just wondering whether we came up anywhere in your research.
The honest answer is if you did, I would have brought it up.
Fair enough.
But that doesn't mean it's invalid. It just means I didn't go down the right medium rabbit hole.
That's fine. So we were actually listed by L2B originally and then delisted. We were the second one on the slide yesterday. I think the very first version of L2B had us at number 2. And then we were delisted after a fun discussion about whether or not what we do is technically an L2. So I wasn't surprised that we weren't in the presentation. But we have a presentation later on with our CEO later on.
Well, then maybe I'll see you there. Maybe I'll update this presentation for next conference.
But well, maybe we will appear later on. We'll see. But thank you. It was a really interesting presentation.
Any other questions?
Yeah. So as it currently stands, whenever I've talked to anyone in this conference, people seem to, have a strong opinion as to whether optimistic rollouts or zero-knowledge rollouts are better, and there are very strong camps. But what I'm actually really curious about is, given the bottlenecks that each one of them have, as time progresses, which one of them is more likely to resolve those bottlenecks? In other words, which one is more likely to be the, to make more sense in other words? Because I guess there are 2 tracks and everyone is trying to actively work on reducing those bottlenecks. And I just wonder which one is the shorter path forward, or if that's even a question that people know the answer to.
Today, optimistic rollups are the ones that really work. We're the only ones that have working proofs. Am I super stoked about ZK technology? For sure, it's the coolest thing. I don't believe in a world where there's just going to be one winner. There's not a clear-cut winner. There's just too much ambiguity today. Like, the probability that there's going to exist, that the ZKs and optimistic rollups are going to coexist in the same environment, I think is very high. What I know today is that optimistic rollups work and that ZK is very, very expensive and very computationally complex. Is it possible? Sure, for sure. Anything's possible in the world. Yeah, of course, I'm bullish on optimistic rollups. I chose to work at Arbitrum.
Okay, thank you.
Thank you. Thank you very much for the presentation. I have a question. On one of your slides, you mentioned simple transactions only for something. Can you talk a little bit more about what that includes and what that excludes at the moment?
I think it was probably referencing the ZK rollups, and because it's so computationally complex to create these proofs, composability becomes really challenging. In composability, meaning, do you want I want this to be able to work on in the DeFi space, in the NFT space, in the gaming space, and I want to be able to work on the same chain and move the same token across all of the chains. In order for something to be functional, like immutable X, it runs on ZK, and it's super cool and it works very well. It's going to be very challenging to put that today into the DeFi space and to move any of the immutable stuff you have into DeFi and then into the more NFT space. So that's what I was referring to.
So simple transfers of assets and tokens, okay, but smart contracts talking to other smart contracts, less okay for now.
Complicated, more complicated.
Okay, thank you.
But all possible.
Okay, thank you. I think we're done with questions, and give us a few minutes to prepare the next presentation. Thank you.